In the last separations class, I reviewed how to perform a material balance on a chemical system. This involved doing a degree of freedom analysis to verify that we had enough information to solve the problem, and then by deriving all the necessary material balances needed to solve for the unknowns. In today's class, I'm going to review the necessary concepts from phase equilibrium. Remember that material balances and phase equilibrium comprise the two parts of any separations problem that's based on phase equilibrium, such as distillation. Don't be too worried if you haven't taken phase equilibrium yet, and if you're just enrolled in it now, because most of what we'll talk about having to deal with phase equilibrium, we already will have covered in material balances. So this should also be review. So suppose that you start with a liquid mixture of component A and component B, and your goal is to separate this mixture into nearly pure component A and nearly pure component B. The way I've drawn it now, I have 6 molecules of component A and 5 molecules of the red one's component B. So I didn't make the math too easy on myself here, but if I wanted to, I need to know what the mole fraction is. So if these are all moles, I've got 6 divided by 11, that is 55%. And the variable, the nomenclature that we use to describe this is X. So X is the mole fraction of component A, and that is 55%. So X is mole fraction in the liquid phase. And XB is then 1 minus XA because I have to add up to 100%, or I could just do 5 divided by 11. And I would say XB is equal to 0.45, and then in parentheses, XA plus XB is equal to 1. Now, if I wanted to separate these components, one way to do it would be to partially boil the mixture such that it reached vapor-liquid equilibrium. So here's a cartoon of what that might look like. As you can see, 4 molecules out of the original 6 of the component A have vaporized and are now in the vapor phase. That leaves 2 behind, and since there are now 6 molecules total in the liquid phase, I would say that my XA is 2 divided by 6, or 33%. Therefore, my XB would be 1 minus that, or 67%. And I could also perform the same analysis on my vapor phase. So the variable that we use for the vapor phase is Y. Y is the mole fraction in the vapor. Mole fraction in vapor. And because I vaporized 4 molecules of blue, 1 molecule of red, I would say that my YA is 0.80 and my YB is 0.20. All right, so note that my physical constraint only applies to either phase. So XA plus XB is equal to 1, YA plus YB is equal to 1. Notably, XA plus YA is not necessarily equal to 1. Now, the major ramification of this is that I now have different compositions in my liquid and vapor phases. So if my goal were to separate these two components, I would be able to do it by forcing the system to come to vapor-liquid equilibrium. So now if I were to just drain this liquid off or collect this vapor phase, so a vapor is very easy to separate mechanically from a liquid, I could then take this vapor off and condense it later, and then I'd have a vapor that is a different composition. Notice that I said initially that my goal was to separate these two components into nearly pure component A and nearly pure component B. I would say that I haven't quite done that yet. 80% and 33% are not really pure components, so why can't I do better than that? Well, remember that phase equilibrium is governed by an equation. So first I have to introduce the concept of Gibbs phase rule. And remember from MEB that Gibbs phase rule is telling you how many intensive variables you need to set in order to specify the system. And the equation for Gibbs phase rule is equal to 2 plus the number of components minus the number of phases minus the number of chemical reactions too, but we don't deal with reactions in this class. That's more for your kinetics course, is equal to your degrees of freedom. So for example, for a binary system in vapor-liquid equilibrium, which is 95% of what we'll cover, only 2 component mixture, so binary vapor-liquid equilibrium. I've got 2 components binary, 2 phases, vapor and liquid, 2 plus 2 minus 2 is equal to 2. For another example, for a 4-component mixture at the triple point, that means vapor, liquid, and solid are all present. Mixture at triple point, I have 2 plus 4 minus 3 is equal to 3 intensive variables that I have to set in that situation. So what do I mean when I say intensive variables? Take our binary vapor-liquid equilibrium example equaling 2. What does that mean? Remember, an intensive variable is a variable that does not depend on size. So for these types of systems, the choices for intensive variables are temperature, pressure, and composition of each phase. And composition of phases. Therefore, for my binary vapor-liquid example, my choices for variables are T, P, XA, and YA. By extension, you could also say XB and YB, but if XA is known, then XB is also known. So I can't specify XA and XB, for example, and claim that Gibbs phase rule is set. So this means that if I set 2 intensive variables, and the most common ones are temperature and pressure, so if I were to go back up to my canister here and say that I'm setting the temperature and the pressure, then I would be able to calculate what my XA and my YA are. Because I've drawn the cartoon like that, we can calculate what XA and YA are, but for the real example where you just have a beaker, you aren't necessarily able to control what XA and YA are unless you set what the temperature and pressure is. So that implies that there's some kind of empirical relationship that relates pressure and temperature to the 2 components. And that empirical relationship is called Raoult's law. So Raoult's law is YA times the pressure is equal to gamma A XA PA star. This is something you'll learn about in phase equilibrium. You learn about the origins of this Raoult's law. So this is Raoult's law written for component A. I can also write Raoult's law for component B. YB times the pressure is equal to gamma B XB PB star of T. Now I have to do some defining of my terms. I've already defined YA to be the mole fraction in the vapor phase and XA to be the mole fraction in the liquid phase. P is absolute system pressure, absolute system P. Gamma I are the activity coefficients. And this is the only new part that you should be unfamiliar if you haven't taken phase yet. And the activity coefficients are equal to 1 if the system is assumed to be ideal. So if the molecules are similar in structure, you can oftentimes assume that these gammas are 1 and they cancel for ideal systems. And if these are not 1, then you have to describe them by some type of model. So in this class, I'll give you the model if you ever need one for the activity coefficient. PA star and PB star, so PI star of T are the saturation or vapor pressures, are the vapor pressures. And to me, vapor pressure and saturation pressure are 2 terms meaning the same thing. Pressures for component I. Remember again that this parentheses T does not mean we're multiplying by T. It just means that vapor pressure is a function of temperature. It's a reminder that when we're looking at Raoult's law, that temperature is included in the vapor pressure expression, or there's some dependence of vapor pressure on temperature. So also remember from MEB that the most common equation that we use for vapor pressure as a function of T is Antoine's equation. So you can find vapor pressures by using Antoine's equation, which says that, and you'll find different forms of Antoine's equation, but the most common one is log base 10 of P star is equal to A minus B over T plus C, where A, B, and C are all Antoine's constants that you can look up in a table. So your MEB textbook has this table of Antoine's coefficients. They're also readily available from a website or from a government repository called NIST, so nist.gov. NIST.gov has a lot of these Antoine's coefficients. And also, just a reminder, whenever you're using a table of Antoine's constants, to always look up the form, because sometimes this is ln of p star, not log of p star, and for the different pressure units. So the Antoine's constants will be reported for a specific value, or for a specific unit of pressure, millimeters of mercury, bar, atmospheres. You want to make sure that you're using the same units as your table does. So just to summarize once again, that you can solve the two Raoult's laws if any two out of the four variables, pt, xa, and ya are specified. You can solve this system of two equations and two unknowns for the other two variables. Because this can be tedious, so say that I set pressure and temperature, and I solve for xa and ya, and it's not something I'm happy with as an engineer. Say I want the purity to be more or less for xa and ya. And if I wanted to go through and change the temperature, the pressure, to try and play with it to see if I can get better purities, that might take a while to do these calculations. So sometimes these Raoult's laws are solved for in graphical form such that they become a lot easier to visualize. In order to do that, you can combine these to make a TXY or a PXY diagram. And an intermediate step in that is to do bubble point and dew point calculations. So the bubble point is defined as the temperature or the pressure. You can have bubble point temperature or bubble point pressure, at which the first bubble of vapor is formed in a liquid mixture. This requires that pressure is being held constant if you're changing temperature, and vice versa, temperature being held constant if you're changing pressure. You can calculate the bubble point constraint by adding the two Raoult's laws together and using the constraint that ya plus yb must equal 1. Now, of course, xa plus xb is also equal to 1, but we're using this as a constraint to solve. So if I add the two Raoult's laws, what will I get? On the left-hand side, I've got yap plus yb times p, so the p can get factored out, and I'm left with ya plus yb times p, and I've already said that this is equal to 1, so I've got p is equal to gamma a xa pa star of t plus gamma b xb, and I can rewrite xb to simplify as 1 minus xa pb star of t. Also, I want to make a note that I'm keeping the activity coefficients, the gammas, in here as well, but if you have an ideal system, which will, most of the time we'll have an ideal system in separations, these gammas will cancel to 1, but in phase, that's rarely the case. And in real life, you oftentimes have an activity coefficient. So I'm leaving it in here just to leave it general. And I'm just going to erase this 1, right, because it's not going to affect the P. So this is my bubble point constraint. Bubble point constraint. I also have a dew point constraint. So the dew point is a similar idea, except this is now the temperature or pressure at which the first droplet of liquid is formed in a vapor mixture. So for this one, I'm going to have the constraint that xa plus xb is my constraint that's equaling 1. And I want to do the same thing where I add two Raoult's laws. And I want to solve first for xa and xb. So if I just rearrange the Raoult's laws, I'll obtain the following formulas. Xa is ya times p over gamma a pa star. And xb is yb times p over gamma b pb star. So now if I add these two Raoult's laws together, my left-hand side is xa plus xb, and I just said that is equal to 1. So 1 is equal to ya times p over gamma a pa star plus 1 minus ya, which is again yb times p over gamma b pb star. And this is my dew point constraint. So let's say I set temperature and I want to solve for pressure at a variety of compositions. I can combine these two dew points and bubble point curves onto the same graph, and that would be called a TXY or a PXY diagram. In the next video, I'll review TXY, PXY diagrams and explain how those can be useful to us in quickly, visually, graphically solving phase equilibrium problems.